So welcome everyone today, particularly Professor Fiona Steele, who'll be speaking to us today. She's from the London School of Economics, and her research interests are in developing statistical methods that are motivated by social science problems. I went through your profile, Fiona, and nabbed out your awards. So she was awarded the Royal Statistical Society's Guy Medal in Bronze in 2008, elected a Fellow of the British Academy in 2009, and appointed an Officer of the Order of the British Empire in 2011 for services to social sciences. And she's speaking to us today on marginal and random effects models. Over to you.
Okay, thank you very much, Hannah, for the introduction, and thank you to Gilbert for inviting me. And I'm sorry not to be able to be there in Belfast, but I will be visiting there in summer for another reason. So I'll get to. All right, so let me begin. So as Hannah said, this is a talk really about marginal and random effects model, but it's for a specific research question, which is sort of how to estimate household effects when you have household panel data. Okay. And I just say this this research is joint with collaborators Paul Clark, Yoni Kua, and Siliang Zhang. And the research is on a topic really that's interested me for probably about 20 years since I started analysing household panel data. So what I'd like to do is sort of begin with some background on household effects in social and health research, previous attempts to estimate them. And then I will talk about marginal and random effects modelling approaches to the problem. So household effect, there's a very large literature on this, particularly in social research, but also in health. Essentially, there is interest in allowing for dependencies among people who live together. And those dependencies can exist for all kinds of outcomes. So in health, both behaviours and outcomes, and in social research, particularly sociology, economics, outcomes like social attitudes. And in this literature, there are sort of three main sort of mechanisms that have been put forward to explain these kinds of correlations. The first is that people who live together share environmental factors. So these could be economic circumstances, they could be just characteristics of the actual house that they're living in, and so on. That's particularly an issue in health research. Another mechanism is that individuals who have similar characteristics may actually choose to live together. Well, and this is, obviously the case when you have, say, couples. So people who are not blood related and maybe have to live together. So actually people who have a choice on whether to live together. Also unrelated sharers. And this is called in the literature homophily. And there's been a lot of work on this in sociology, mainly focusing on couples. And then the third mechanism is more of a sort of a causal process where people influence each other over time, the longer they live together, and this leads to dependencies in their outcomes.
Fiona,
yes.
you're just having issues in seeing your screen.
Oh, you can't see it. Oh.
No, we can. Full screen. If you could go to full screen, that might solve it.
I think I have, but thank you for that.
Sorry to interrupt you.
No, not at all. Well, can you see anything at all?
Yeah.
We can see half of your first slide.
We see that looking at the screen, we see the left-hand side of half of your first slide. We see the economic and seems that there's a margin, and then we see marginal and rand. We see as far right as RAM.
Oh. Can you see the title slide now? Is anything changing?
No.
Oh, okay.
Yes, unshare and then share again.
Okay, let me try.
Yeah, you're very good. We see you very clearly.
But I would like you to see my slides. So let me try again.
Great,
Perfect.
great.
Can you see that?
Yes.
And now
yes.
if I move on to the next, you can
Yep,
see that all
perfect,
right?
perfect.
Good. Phew, that's a relief. All right, all right. So I hadn't got to any equations, so which you really need to see. So that's good. All right, so just going through the sort of background, what are the mechanisms that might lead to household effects? So that the third point there was just to say that as well as there being interest in household effects, in epidemiology, there's a lot of interest in area effects. And there's been some concern that if you don't account for household effects, then those area effects may actually be picking up some of the household effects, so giving the impression of larger area effects than there actually are. So much previous work has really been to look at this problem and to sort of try to estimate household effects has been based around cross-sectional data. And that is actually just often from household panel data, because that's the main source of household data, or if individuals within a household, they will just take one wave of the panel study. So obviously not using that data to its full potential. If we use the multiple waves, then that allows us to then separate out individual and household effects and area effects as well, if they're also of interest. So, you know, most panel studies will focus only on individual effects. And we also have the opportunity to look at these within household associations, particularly, you know, how they might change over time. But some previous research has not been entirely encouraging on this as a you know, a useful thing to look at. So there's this very influential paper from the mid-80s who concluded that efforts to define a longitudinal household are just bound to be futile. The second quote there is about the UK Household Longitudinal Study, also known as Understanding Society. And one of the authors there, Nick Buck, was a director of the study for a very long time. They say it's not a longitudinal study of households, since households have no coherent existence over time. So, you know, these might be rather off-putting statements, but actually our approach doesn't require the definition of any sort of longitudinal household. In other words, we're not going to need to define, you know, what kind of household changes lead to a new household. So we kind of, I think that's been a concern with a lot of that literature. So we would actually not disagree with either of these two statements, but you have to view the problem in a different way. And as a result of this kind of rather off-putting comments about trying to look at household effects, people have largely looked at individual effects, and they will try to include covariates, time-varying covariates in their models that capture changes in household circumstances over time. So these previous effects, so as I mentioned, a lot of the work has really just focused on cross-section. Then that gives you a nice nested two-level structure, individuals within households, and you could just proceed as usual, perhaps using multi-level models or marginal models. Using longitudinal data, the first approach there I highlight, it is essentially cross-sectional in that the outcome is cross-sectional, but the longitudinal data will be used to define covariates. Another approach, and this is mainly when people have been interested in couples, is to focus on those couples who have stayed together over the entire observation period. But if we want to extend that to look at households, then that's going to give us a very restrictive sample of households. Now, the third approach, and this is probably the only sort of serious attempt to look at household effects in longitudinal studies, is to use what are called multiple membership random effects models. And I won't go into these in details. One of the papers that I'll mention later does have a review of this, but essentially this approach includes a weighted combination of the effects of all the households that a person has belonged to over the observation period. The difficulty is that, usually these panel data, they're sort of left truncated. You only start to observe people when they enter the study. That might not be necessarily a meaningful time point in terms of the process that you're studying. Another issue is that you have to choose these weights. They are not, it's not possible to estimate these from the data. So that involves some sort of arbitrary decision. So in this talk, I'm going to talk about two approaches. The first one is a marginal modelling approach, and that has previously been published in 2019. But I want to focus more on some work that's in progress that goes back to a random effects approach. So trying to look at that multiple membership model, but trying to overcome some of the issues with that. And the reason I want to talk about the two approaches is that they both involve some key concepts that are in common, and also it allows me to just to contrast the two approaches, because it really does depend on your research question to a large extent which of these two approaches you might use in practice. So let's begin with a sort of general panel model that you might fit to longitudinal data. So here we're assuming we just have a linear outcome y measured at wave t for an individual I. We've got the usual covariates, which could be time varying or specific to an individual. And then we have some residual RTI. And we can look at covariances among these outcomes. Now, traditionally, the focus has been on the within-person correlation structure. But what we're interested in here is additionally the between-individual covariance structure, conditional on these covariates for the two observations that we're looking at. So there's two sort of broad approaches to this. The marginal approach involves imposing some correlation structure on the RTI. Well, it's a direct parameterization basically of the covariance matrix. The random effects approach involves sort of decomposing the residual into individual, household, and perhaps other components, sort of representing these sort of different sources of variation. So I'll start off with the marginal modelling approach. And what we can do is define a generalized linear model which has three features. Now we've got these sort of three equations here, or three models. The first one is the traditional model that we would have for a generalized linear model, is we're modeling the expectation of an outcome as a function of covariates, but that can be extended to model the variances of these outcomes or the correlations among outcomes. Now, to look at correlations, we need to define some clusters to make this a manageable problem, because if we try to estimate freely the covariances between any pair of observations, then that's really going to be computationally infeasible. So we have to define these clusters. So traditionally, when you have longitudinal data, those clusters would correspond to individuals. So we're going to extend that idea to allow us to look at correlations among individuals who are co-resident or who have been co-resident over the observation period. So the part of the model that we're most interested in, that I'm going to focus on, is this correlation model. So here we're modeling the correlations between every pair of observations within these clusters, which I'll define in a moment, as a function of covariates X3. And having defined these clusters, then this this marginal model can be estimated using existing methods, sort of general estimating equations called the sort of second order GEE, and that has been implemented in an R package, for example, GEE pack, which is what we use for estimating these marginal models. So the key point then is, how do you define clusters? And this involves what we refer to as a super household. These are the clusters that we refer to are what we call super households. And we call them that because we're going to have multiple households within these super households, basic clusters of households. And they're going to have these properties. So I'll focus on so we're actually viewing the process of household change over the observation period is like a social network that evolves over the observation period. So these super households have to satisfy a number of properties. First of all, we want to allow for a link between two individuals if they have ever lived together. We also allow for links between individuals if they might live together in the future at a given point in time. If, on the other hand, individuals are from different super households, then there's no pathway between them. So we don't allow any correlation between observations for individuals in different super households. And also, observations on the same individual over time are in the same super household. And that's important so that we can allow for autocorrelation. So let me just give you an illustration of what we mean by a super household. So what we've got here is household change over 3 waves. So we start off at wave 1 with one household. We've got a man and a woman, a couple, and they have an adult child, age 17. Wave 2, the couple have split up, and the child has remained with their mother. And then at wave 3, the man from wave 1 has repartnered. And also the son has moved in with somebody else, and another male. So what we have over time here are 5 distinct households, but they are linked because they are sharing individuals. We can look at this in this sort of graphical structure. So here we have all the paths among the 5 individuals in these 5 households. And I've just used dashed lines here to represent the situation at wave 3, where they're no longer living together, but they have lived together at either wave 1 or 2. And it's the super household cluster is defined as the set of households and the observations within them at the final wave of observation. Okay. And just to look at some of the reasons why a household may change over time, these are sort of there's sort of many demographic events. They're not mutually exclusive. So, for example, we saw an example there where an adult child leaves home and they form their own home. That could be because they form a partnership. So that would be the first and the third reasons there that are co-occurring. So let me just, and I won't go through this in detail, you'd be glad to hear, otherwise we may be here for the rest of the talk. But I just wanted to illustrate the complexity of household change in a real data set. So this is data from the British Household Panel Survey. That has now been subsumed within the UK Household Longitudinal Study that started in I think about 2010 or so. Anyway, in this study, and what we've got here are rows corresponding to individuals and columns corresponding to waves. So here our observation period is 17 waves. And at a given wave, everybody who is co-resident is in the same colour, but I've had to reuse colours because there's so many different households over these 17 periods. So let's say at wave 1, we've got a couple and they have 4 sons. At wave 2, the eldest son forms a partnership and they have a young child. These households then stay static for 4 waves, and then at wave 6 we've got another son leaving home, forming a partnership and having a child, and so on. So if we look at the very end, wave 17, the couple is now living on their own, and then we've got all of the sons and their families. Okay. So the marginal modelling approach, so this involves this sort of direct modelling of the covariance, or actually the correlation among observations for individuals who have been co-resident or are currently or may in the future be co-residents. And there are a number of substantive questions that we can ask that sort of stem from looking at these correlations. So I won't go through all of them, but a simple question is, well, what is the extent of within-person correlations? That's the typical question we would ask about autocorrelation. The other 3 are all about correlations between individuals. So, for example, if I just pick up the 3rd one there, we might expect that the correlation between individuals may persist after they stop living together, but perhaps it starts to weaken over time the longer they live apart. That allows us to sort of get some handle on whether it's a selection that has led a couple, say, to live together rather than one influencing the other. If it's a selection, then you might expect correlations to persist, you know, when they stop living together. And the 4th one there is, well, we might expect correlations to depend on the relationships between 2 individuals. So I'm just going to briefly talk about an example and just give you some estimates just to show you the kind of information that you can get from this approach. So these data are from the British Household Panel Survey, and the outcome here is attitudes towards gender roles, and we have up to 9 waves per person. And the model for the correlations among observations within super households depends on a number of indicators. So these are covariates that characterize the connection between 2 observations within a super household. So one of these indicators sort of indicates how far apart the 2 observations are in time. The other set of indicators measures the co-resident status of 2 individuals, so these 2 particular points in time. And the 3rd one is a set of indicators for the relationship, whether they're the couple, parent, child, or perhaps they're just sharing and there's no biological connection between them. So let me just give you a brief snapshot of the kind of results you get from this model. So you get a lot of parameters for the correlation model, but what I've done here is convert these into estimated correlations. And I'm focusing here on how these correlations depend on the relationship of the individuals for a particular pair of observations. And these estimated correlations are for a pair at the same wave. So we've kind of not looking at temporal correlations here. And we're showing correlations here before and after, including covariates in the mean model. So you can see some changes after accounting for covariates. The main covariate actually that changes the correlations is the age of the 2 individuals. So for example, this one here, because unrelated people, they tend to be of a similar age. So you imagine young people living together. So when we account for age, we're explaining quite a lot of the correlation. A lot of their correlation is due to them being of a similar age. Whereas here, parent-child pairs, they have an age disparity. So when we account for age, then we're actually seeing the correlation go up because age is like because here the sort of age is being masked, the age effect is being masked beforehand. Okay. So we can get estimates like this for all the indicators that we include in the model. All right, so let me now move on to the random effects approach, sort of motivate why we don't just settle for the marginal modelling approach. Well, what are the advantages of the marginal model? Well, at a sort of basic level, then they adjust for clustering. So we want to ensure that our standard errors are adjusted for not only clustering by individual, but also we would expect there to be perhaps some underestimation of standard errors, particularly for household level covariates, if we don't allow for clustering by household. But I think more importantly is that the marginal model, gives us this information about the nature of between individual correlations, which is of substantive interest. But there are some limitations. The first one being that we don't get a partitioning of the variation into different sources. So we might be interested in, what are the household effects relative to the individual effects. Also, this approach doesn't really extend if you have sort of higher order clustering. So I mentioned in epidemiology, there's a lot of interest in looking at area effects as well as household effects. We can't do that within the marginal modelling approach. And that's because super households are not nicely nested within areas because they're including individuals at different points in time who may live in different areas. So we don't have a nice nested structure there. And then finally, a sort of more technical issue is, and a common criticism of GEE, which is that the within cluster correlation matrices, the estimated matrices, may not be positive definite. Although I have to say in all our applications and simulations, we have not found that to be a major problem. So I think the main motivation really is the first two of those points after the but. So we return to the linear panel model that I started with, and we have our residual RTI, but now rather than modelling directly the correlations among the RTI, what we'll do is we'll partition the residual into different components. So here we've got components for the individual, the household, the area, and then we have this sort of time varying residual left over, the ETI. And for those of you familiar with multi-level modelling, you may think, well, these subscripts don't look particularly standard. And that's because we don't have a nested structure here. So I'm using an alternative notation, which is used quite a lot in cross-classified and other non-hierarchical models. And here we want to indicate, for example, that the household effect it changes over time according to the particular household that a person is in at a given point in time. Similarly, a person may move area over time. So again, we want to recognise that in our definition of the area effects. We're going to make the standard assumptions about these random effects and the residual E. We assume that they're normally distributed. And what we would normally do is assume that all of these were IID, but that wouldn't be appropriate here because the households may have some individuals in common. And so we're going to relax the assumption that the household effects, the V's, are uncorrelated with each other. So just to reiterate, we've got this household effect, which may change according to time. So that's the VHTI. So this index here, the HTI, is essentially a household identifier. And this identifier will change anytime there is a change in co-residence. So what we do is we compare a person's co-residence across 2 waves. And if there's been any change at all, then they're assigned a new household ID. Sometimes these changes are temporary. So you might have, say, a couple who are living together, maybe an adult child returns home for a year or 2, then they leave. In that case, the couple's ID will revert back to the ID they had before the child joined them. So this is then quite easy to define. We're not having to make decisions about what kind of household changes should lead us to give a new household ID, which was the main sticking point that I think early researchers had about estimating household effects with longitudinal data. So in our approach, we have 2 households, HH prime. If they're in the same super household, then they're going to be linked in some way through co-residence. They may not actually, so they're linked through co-residence, but yes, say that could be indirectly, because it could be that individuals in H have not actually lived with H prime, but the 2 households have in common someone who has lived with somebody in that household. Okay, so what we're going to be doing here is again defining a correlation model, but now, unlike the marginal case where it was a correlation model for a pair of observations on individuals at 2 waves, these are correlations for 2 households within the same super household. And these covariates here are going to be indicators of how these 2 households are connected. The estimation approach, well, we use MCMC methods, which are very flexible in general for multi-level modeling, but particularly when you have non-hierarchical structures as we have here. But we have to adapt the usual algorithms here because of this correlation that we want to allow for between household effects for households in the same super household. So these random effects for the same super household, they're sampled as a block. And we assume that the household effects follow a normal distribution. This is the covariance matrix omega for the household effects in super household S. And we decompose that as the between household variance, sigma squared V, and the correlation matrix. And this correlation matrix has these parameters, which are representing the covariate effects on the correlations. And it's to ensure that this the estimated correlation matrix is positive definite, then these the parameters of the correlation matrix have to be sampled in a certain way. So the algorithm includes a Metropolis Hastings step. So basically, if a set of gammas is sampled, which gives a non-positive definite correlation matrix, then that set is rejected, and another one is sampled. And this algorithm has been implemented in our package, and when we get it published, then that will be made available. Okay, so before I go on to an application, just wanted to show you some simulation results. So what we've done here is simulate from our proposed model. So that is model 3, the one where we've got these, and here I've ignored the area effects just to keep things a little simpler. So we've got these 3 components of variation in the full model: household, individual, and wave. And in model 3, we're allowing the household effects in the same super household to be correlated. So if you like, we're generating from this what we think of as the correct model. And here we have the true variances for these different classifications, and they sum up to 1. So these can also be then interpreted as the proportion of variation at each of these for each of these classifications. And we've generated data with 20,000 super households, and we're actually generating from the generating these data from the actual data that we analyse, which is from this UK household longitudinal study. I'll talk about the data in a moment. That's about half of the super households that we have in the real data. So here we have the mean estimates from 20 replications, and we were interested in here to see what happens basically if you ignore the household effect. So that's in model 1. So that's if you fit the usual individual panel model. So here, then, as expected, that household variance, well, it's got to go somewhere, and it gets split between the individual level and the wave. It doesn't go entirely to the individual level, and that's because individuals are not nested within households. If this has been a 3-level hierarchical structure, then the effect of missing a level means that the variation just gets absorbed into the next highest level. So here we've got this sort of split of the variation. So we would overstate then the contribution of the individual. Whereas in model 2, we're allowing for household effects, but we're not allowing them to be correlated. So this does a lot better, but we've still got some bias in the estimates of the variance components. Just to summarise the other results, we also find that if you've got household level covariates, model 1 in particular produces underestimates of their standard errors because you're ignoring an important part of the dependency. And the biases that we're seeing here, both in the estimates and in standard errors, that will decline as the intra-household correlation gets smaller. So it makes sense. If the household effects are very small, then we don't really have a concern here. And model 1 would be perfectly reasonable then to fit. So let me now just go through an application just to show you. I'm going to be focusing again on the model for the correlations. So data from the household longitudinal study. I mentioned the BHPS earlier. This is its successor. It's much larger, 40k households. It includes Northern Ireland. We're going to be looking at 2 outcomes here, 2 health outcomes, which I'll just call physical and mental health. We've got a number of covariates in the model for the mean of these 2 health outcomes. So we're fitting separate models for these 2 outcomes, and the interest is then in comparing the 2. I'm not going to show you the estimates of these covariate effects. I mentioned the super household is going to be defining the clusters again here. These are taken at the final wave of observation, which is wave 11. We're defining areas after some investigation of different area classifications as the sort of the lower super output areas from the census, and there are just some information on the size of the analysis sample, so quite large. Now, in the footnote there, just an important point here is that when you're in the data preparation, when you're sort of deriving the super household and the household ID, it's important not just to use those individuals that respond at a given wave. We also have information from a complete enumeration of the households, which is going to be typical in a household panel survey, often called the household grid, and we're using that data to derive the identifiers. Okay, because very often you may only say you've got a couple, you may only have one person in that couple who responds. So if you just look at the data on respondents, you may think there's been a change in the household, but there hasn't if you look at the household grid. So the covariates. So these are, as you remember, covariates for the between household effect correlations. So these are now describing the connection between a pair of households. So they can be indicators of whether there is a sort of what I call a partnership link between the two households. So whether these two households share partners currently or in the past or in the future. Another set of indicators are for whether there is a parent-child link between the households. So whether a member of one household is the parent of a member of another. And then we have just a measure of how much overlap there is between the two households in terms of the number of individuals, so the proportion of overlap. Now, these indicators of partnership and parent-child links, they account for the vast majority of all the household pairs. Most of the changes, if you like, that lead to the demographic changes that lead to changes in household structure are essentially partnership events or events where we've got parents and children, children leaving home or entering home, or births. All right, so now just to show you a few results. And so we've got two stacked bar charts here. On the left, physical health, and the right, mental health. Let me start with the one on the left because they're really showing the same thing. What we've got here are the components of variation, and this is from a model where we don't have any covariates in the mean part of the model. On the right, we've got the full model with the household effects, and on the left, we've got a model where we just ignore household effects, and we've got only individual effects and area effects. So in the analysis, we've reintroduced the area effects. So a few points to note here, just looking at the model with all four components of variation, you can see that the area effects are tiny, and this is fairly consistent across studies of health. The household effects are quite sizable, not as large as the individual effects, but still, quite a lot of correlation among co-residents. And on the left, we've got what happens if we ignore the household effects. So there we can see that in this case, most of the household variation gets soaked up in the individual variance. There is also an overstatement of the area effects. It's quite hard to see because the area effects are so small, but actually you can see, we find that the area effects, although negligible, half really if you account for household effects as well. Turning to the mental health case, we see here that the household effects are somewhat smaller. That I think might be expected, because you may expect that there would be more correlation in physical health due to perhaps shared environment. Also, there could be genetic factors for family members, shared lifestyle, and so on. But still non-negligible household effects for mental health. And a lot more variation, which is sort of just time varying, that we don't explain by individual or household effects. Okay, now moving on to the correlation part of the model. And I won't lie, this is a little tricky to interpret, so I've tried to break it down. So the output from the correlation matrix is a set of coefficients, basically, for the correlations. They are somewhat difficult to interpret because you have some sort of overlap in different kinds of link between households. So what we've got here are what I've done is classify the pairs by all the possible combinations on these indicators of partnership and parent-child links, and there are in total 35 of those. But 9 of the patterns account for almost 90% of all the pairs. So a lot of these are very rare. And I'm just going to show you the sort of top 5 kinds of links that we see between a pair of households. And what we've got here for the first type is the estimated correlation between the two households of this type. Now, it's the mean correlation, because there is some variation for the pairs, because the amount of overlap between the pair may vary even within this category. Okay, so what we've also got there is the mean proportion of overlap. So for this first type, we've got on average, we've got an overlap of almost 65% in the members of the two households, and this first type accounts for 14% of all the household pairs. So what is this type? Well, it's two households that have basically a parent-child link. So one of the households has the child, and the other household has both a parent or both parents and the same child, and it's an adult child. There could be other members of each of these two households, but the key thing is that the household shares at least the adult child. So there we see quite a high correlation on average between the effects for these two households, and that's true for both physical and mental health. The second type that I'll talk about, this is the second most common. Here, again, it's a parent-child link, but now the two households do not share any individuals. So we've got the parent's household and the child's household. So then we have a zero overlap between them. Still quite a high correlation. So even when the parents and children stop living together, there's still quite a high correlation in the effects of their households on their health. Now here we have a pair of households where we've got again quite a high overlap, and this is where you've got that the households are connected by there being a birth, basically. So you've got say parents before a birth and then parents after birth. There could be single parents as well. They're grouped together here, and again quite a high correlation between their effects. Now, this one is where we've got a partnership link. So here we have a couple in the first household, which is the household that is formed first, and then the couple split, and the second household includes just one of the individuals. So again, there is some overlap between in the household. They share at least one individual of the couple, but there could also be children in common. This correlation is much lower than we have for the parent-child. And then just one more. This is when there is no family link between the two households, but it's where you've got, say, typically groups of young people living together, and they're linked and they're different because perhaps just one person has moved in, or another or someone has moved out. So we've got quite here the overlap is quite a bit lower, but we've got moderate correlation here between the households. So this information can sort of tell us then about the kinds of household change that kind of lead to, if you like, to the most sort of material changes in the household. In other words, leading to very different household effects. But in all of these cases, I guess, apart from, or at least to from a lesser extent, although we've got quite major changes in the households, their effects are still quite similar. Even when in this case, they don't actually have any individuals in common. Yes.
Can I ask about this table? We have physical health and mental health measured somehow.
Yes.
Yeah. So you've got some scale for that. Yeah.
Oh yes. Yes, I didn't go into it. I just mentioned that. Yes. So these are measured by a set of indicators. It's quite a commonly used scale in self-rated health, the SF-12. So there's sort of 12 items altogether, but they're split between physical and mental. And they have been what I've done is a sort of principal components analysis for each of those scales, and what we've got is a standardized score. Okay. So yeah.
Can I ask then, does the model allow you to, I'm sure it does, allow you to make adjustments for altering the covariate profiles in these households? Or is this it says it's the mean predicted between household correlations. So I'm wondering if we can have adjusted figures for the correlation.
So adjusted for what?
Well, for anything you might like to adjust for.
So
well,
we have.
Go ahead.
So we have covariates in. So we have the mean models, models for the mean physical and mental health, and they have covariates in them. So these correlations are adjusting for those covariate effects. So we're adjusting then for the fact that physical health, and mental health depend on age, they depend on gender, ethnicity, all kinds of demographic and some socioeconomic things. So those characteristics are in the model, and these are correlations between the household effects after adjusting for those. So these are, if you like, these are household effects that are the effects after accounting for these covariates in the model. Does that answer your question?
Yeah. So you can vary that by altering the models, the underlying model.
Yes. But only in terms of the covariates that you include. That's right.
Yeah. Well,
yeah.
One wonders how dependent is the result on the level of adjustment, for example.
Now, these between household correlations, they do change a bit depending on what household level covariates are included in the model. So these are adjusted, but if you didn't account for, so I've got actually two household characteristics. One is the housing tenure, so whether the house is owner occupied, social, private rent. The other is household income. Household income doesn't have a very large effect, but accounting for household tenure, that does actually account for quite a lot of the household effect, but primarily for physical health. That doesn't explain much in the mental health. So the physical health results there, those correlations would be somewhat different, probably a little bit higher if we hadn't accounted for this housing tenure. But I haven't got the results here to show you. But that's something you can certainly, something that would be of interest to compare.
Thank you.
Okay. Okay, let me just show you some more results, and then I just make some kind of summary remarks. So what we have here are the intraclass correlations. And whereas when we typically analyze panel data, we just have the intraclass correlation for the individual. So this is just the correlation between responses for the same individual at different time points. So here, and this is conditional. So following on from Gilbert's question, this is after controlling for a number of covariates for physical and mental health. So these are the sort of temporal correlations. And then we've got correlations between individuals in the same household. And so here we have a higher correlation for the mental health. That looks different to the earlier stacked bar chart I showed you, where you had a larger household effect for physical health, and that's because they were unconditional. There was no adjustment there for any covariates. So it just so happens that the covariates that we have do a better job of accounting for household effects on physical health. And here we have the correlations between two different households from the same super household. And so these, as you might expect, these correlations are much smaller. But now there is going to be some variation because it depends on how a particular pair of households are connected. This is, these covariate effects for the household effect, for the between household correlations. So here we've got the mean ICC and the standard deviation. And then finally here we've just got the correlation between observations from where the only connection essentially is the area, and these are very low. So just make a few concluding remarks. So first of all, the random effects approach. So there are a lot of ways, of course, that you could extend this. So as usual with longitudinal data, we may want to, particularly if we're looking at some kind of growth process, then we could include random coefficients on time. I've not mentioned it there, but of course there are other ways of allowing for autocorrelation, and that could also be an important extension, because what we've done here is assume that the correlation between any pair of measurements on the same person is equal. We could also define a model for the between household variance. We've been focusing on the correlation, but the variance itself may be of interest, because it could be that household effects depend on the characteristics of the household. So maybe these effects are stronger for some types of household than others. We could explore that by defining a model for the between household variance. And then finally, extension to categorical responses. This would be quite straightforward to do with our Gibbs sampling algorithm for at least for binary or ordinal responses, but that hasn't been done yet. And then finally, well, which would I choose, marginal or the random effects approach? Well, as ever, when you're choosing a method, this often depends really on the research question. So just to recap, the random effects model, it allows this partitioning of variance, and we could have multiple levels here, which would be quite straightforward to incorporate. Also, the random effects model, we're looking at covariate effects on the between household correlations, the between household effect correlations. In the marginal model, we're looking at covariate effects on a different type of correlation, which is the correlation between two observations, you know, at a given time point and for a given individual. So they are different, and as it depends which of those you're most interested in. I would say these are probably easier to interpret. And then there are some other considerations. One is of course, speed. Marginal model, that is extremely quick to fit in GE-EPAC, even for very large data sets. The random effects approach, we're using MCMC, and that is much slower. And also for these models, particularly when you've got a large number of covariates in the correlation model, you need to run for quite long chains for convergence. So it's really important to sort of run, you know, parallel chains to make this more efficient. And then finally, and not a trivial thing, is the data preparation. Which is, as anybody who does applied research knows, can often be a largest part of the research process. I have to say, deriving the covariates for the between household correlations is quite tricky, and that's because you have to look across all the individuals in the two households to determine what the connection is between them. It's much easier in the marginal model just to look at the connection of two particular observations on individuals to look at what their connection is. So, but so when our paper is published, we would be sharing our code for doing that, which could be adapted to other data sets. All right, I will finish there. Thank you very much.
Okay.
So I just stop. Oh.
Yes. Yeah, but
Should I stop sharing?
Yeah. Ah, that was a tour de force of this particular area. I'm not so familiar with these kinds of household sets of data, but I'm interested to know in how the time effects are handled in the model. In the random effects model, it seemed to me that at the end the error is just normally distributed. That's fine. So that if I could ask, in terms of the longitudinal processes, you're assuming some form of independence by that stage.
Okay, yes, so we're allowing, it is quite simple what we're doing in the random effects approach. It's quite simple. We're just allowing for a correlation between any pair of measurements on the same person, and we're assuming an equal correlation structure there. So
compound symmetry.
That's
So
right.
you might be able to extract more from the data set by trying to model the covariance structure, the longitudinal
That's
covariance
right.
structure. Yeah.
That's right.
Another possible extension.
Yes, absolutely. And so if you've got a growth process, one way to do that is with a random coefficient on time, but say more generally, yes, you may just want to say specify an AR1 structure or something, and that could be done. It's much easier to do in the marginal model, modeling approach, because you can just specify indicators essentially for the time lag between any two observations. But that is, yes, certainly something that should be done for the longitude, for the random effects framework. Yeah.
Do we have
Any questions? Any questions for Fiona? Might be, I'm not sure.
okay.
Yeah, thank you very much for your talk. I saw you mentioned earlier that you looked into people's opinions on gender roles. I think it was with the marginal model. Have you looked at any, or have you any plans to look into things like how political views would be affected by household effects?
I haven't looked at that, but and I haven't seen literature on that either. Well, I have. I think I've seen a paper on household effects on voting. That's looking at household effects cross-sectionally, but not on political attitudes, and that would be really interesting. Yeah. But no, haven't done it, and I think that would be yeah, just particularly looking at whether trying to get at whether you've got this kind of homophily, a selection where people with similar attitudes are more likely to live together, particularly with couples, or whether they influence each other over time. Oh yeah. Yes. Yeah.
If someone online that like to ask a question.
Yeah.
Oh, Fredo, I think. Huh. Hello. I can't hear you.
Can you hear me now?
Yes, yes.
Okay. Hello, Professor Steele. Thank you very much for your talk. I'm Alfredo. I'm a PhD student here in Italy.
Hello.
So I wanted to ask you, so you said like the mixed models effect was trained with an MCMC. So you sort of have de facto, you have this empirical distribution for the coefficients that is given by, let's say, the last, say, 1,000 samples from the MCMC chain. So I was thinking, of course, you could exploit those samples to have a sort of confidence bands or prediction error bands. And have you thought about that? And if so, was that empirical distribution that you get, for example, from 1,000 last samples of the MCMC chain actually normal? Because of course, one of the, sorry, not normal, a T distribution, because I'm guessing in this parametric model, you're also assuming that the coefficients are T distributed, right?
Yes, we have looked at that for all of the coefficients, both in the mean model and in the correlation model, and they are fairly symmetrically distributed. So looking at the usual sort of 95% credible intervals for those. But your question does also, I think it would be useful to put confidence bounds on the actual predictions. So those predictions that I showed at the near the end there, or also on the intraclass correlations, and that would be one of the big advantages of an MCMC approach. You could get some intervals on those. We haven't done that yet.
Okay, but for the MCMC, you don't have to assume a prior distribution, right? This is not a Bayesian model. So you sort of
yes.
get the advantages of a Bayesian model without having to specify prior in a way.
Yeah. Well, we're specifying well, non-informative priors. Usually we don't have we don't have any prior beliefs that we incorporate in the model. So yeah, we're assuming the usual kind of normal priors for the coefficients, and I think inverse gamma for the variances.
Okay, thank you very much for your answer.
Thank you.
Yeah, I think the point you raised, about no prior beliefs. It's because in some ways we haven't seen data like these before. So that is, as the new modeling techniques come through and new theoretical structures, it will take some time for people to become familiar with this kind of analysis and to be able to see how these effects pan out. And then there may be some social insight, some scientific insight into what effects you might expect. We found this with, although in econometrics, what I'm about to say wouldn't be true, but in biostatistics, we found we weren't used to modeling innovation variances. So had little idea as to how they might perform. It's the same kind of situation, I think.
That's right. No, I think it's a good point. If you're developing methods that sort of allowing really new questions to be asked, then you're not going to have any real sort of priors on that. But yes, over time, with sort of replication, then you may have a better sense of that.
Any more questions? Okay, there's no more questions. So thank Fiona again. Thank you very much.
Yeah.
Thank you very much. Thank you again for inviting me.
Yeah, our next talk is the 6th of December with Chris Jackson coming in person. So that'll be exciting. Thank you very much.
Thanks,
All
Steve.
right, then.
Very much for coming. Very
Bye-bye then. Bye.
Bye-bye.
See you in June.